Hello and welcome back to the Science of Concrete Materials class. This is lecture number 17 of the class, and we are still on the SCMs topic, supplementary cementitious materials. Okay, so we already had one lecture, which is lecture number 16 on this topic. So now that we had a broad view of the SCMs, let us look in details of each of the common materials used. We will start with the pozzolans and then we will discuss slag. This table here shows the common pozzolanic materials classified as natural and byproducts. We already have touched upon some of these materials. If you remember, the natural materials we have, the unaltered volcanic ash, and the active components in these materials are the aluminosilicate glass. We have the weathered volcanic ash, such as the tuff, trass, and the like, which we have the aluminosilicate glass and zeolites. The pumice and the active component is also aluminosilicate glass. Diatomaceous earth, the active component amorphous hydrated silica. The opaline cherts and shales and the active components in these are the hydrated silica gel. The second category in the common pozzolanic materials are the byproduct materials, such as the fly ash, class F and class C. In class F, the active component aluminosilicate glass. In class C, calcium aluminosilicate glass. Remember, class C is high in calcium. That's why it exhibits some cementitious behaviors. The second one is silica fume. The active component is amorphous silica. The rice husk ash, also amorphous silica. And we have the calcined clay or the metakaolin, the active component in which being the amorphous aluminosilicate. Okay, so the naturally occurring pozzolans were used extensively in the construction of mass concrete, basically for hydraulic structures in the western United States during the 1930s and 40s. However, the first modern use of pozzolan in the US dates back to the early construction of the Los Angeles aqueduct between 1910 and 1912. And in addition, pozzolans were used in the Golden Gate and San Francisco, Oakland bridges. These projects required sulfate resistance as well as reduced heat of hydration. The Bonneville Dam in 1935 was the first of many mass concrete dams to use natural pozzolans to control the temperature rise during hardening. Basically, local materials were used for this purpose, mostly local materials. Okay, as for the byproduct pozzolans, the most commonly used today include the fly ash, which is basically residue of powdered coal after burning in power plants. Silica fume, which is a byproduct in the manufacture of silicone, metal and alloys. And we have also the rice husk ash. This is a high reactivity pozzolan obtained by controlled calcination of rice husk. In the last one is the metakaolin. This is obtained from the calcination of kaolinite clay in the range of 700 to 900 degrees Celsius. Okay, remember I talked about a Pozzolanic reaction during the previous lecture. So let us really define the Pozzolanic reaction and differentiate it from a hydraulic reaction. If you remember, I indicated that some materials exhibit hydraulic behavior, that means being cementitious on its own, versus pozzolanic, which is not. But let me here just make the distinction between a hydraulic reaction and a pozzolanic reaction. The pozzolanic reaction is a chemical reaction with calcium hydroxide, lime, and water that leads to the formation of a cementitious product, like the calcium silicate hydrate. And that's what these materials contain in the amorphous silica. It reacts with lime to basically result in the formation of calcium silicate hydrate. So it does not have cementitious characteristics on its own. On the other hand, the latent hydraulic reactions, these are chemical reactions with water that leads to setting and hardening of the material without any help needed. Okay, so let's look more at the pozzolanic reactions. Following the Portland cement hydration reaction, where basically the hydration of C3S or C2S with water, where calcium silicate hydrate and calcium hydroxides are the resultants of that reaction. The amorphous or glassy silica, which is the major component of pozzolans, reacts with calcium hydroxide formed from the hydration of the calcium silicates as above in equation 1. The principal reaction in this case is as follows. We have the calcium hydroxide reacts with that glassy or amorphous silica in the pozzolan in the presence of water, of course, and the result will be a calcium silicate hydrate gel or calcium silicate hydrate, which again, this is the product responsible for the strength we get from the concrete. This reaction number 2, call it, and this is a slow reaction typically. So when fly ash, for example, and natural pozzolans are used, the composition of the calcium silicate hydrate is not very different from that formed in regular hydration of the cement. Although generally the calcium to silica molar ratio is slightly lower. However, with very reactive pozzolans of high silica content, such as silica fume and rice husk ash, the calcium to silica ratio is significantly different, being close to 1. If you remember, the calcium to silica ratio and resulting from the hydration of C3S and C2S is about, I think, 1.5 to 2, if I remember correctly. This one, the molar ratio being close to 1. And also the water to silica ratio is slightly lower in that case. Also, something to mention about the reaction of these pozzolans, small quantities of reactive alumina in a pozzolan generally substitute for silica as part of the calcium silicate hydrate. When a pozzolan has appreciable quantities of reactive alumina, for example, natural pozzolans or the calcined clay, the metakaolin, a separate set of secondary reactions can occur, leading to the formation of the calcium aluminate hydrate, as you can see here in equation number 3. Calcium hydroxide react with the alumina present in some of these pozzolans, plus water, we get the calcium aluminate hydrate. We have to be very careful though, because this reaction may have adverse effects since it increases the potential for the sulfate attack. Be very careful when certain materials high in alumina are used. Okay, equation number 2 in the above, in the previous slide, is basically the primary pozzolanic reaction. And its kinetics are more similar to the slow hydration of the C2S. Remember that. So the heat of hydration, the heat of reaction is about 12 kilojoule per mole of calcium hydroxide compared to about 43 kilojoules per mole of C2S. So the reaction is very slow and gives off less heat. So the addition of a pozzolan has a similar effect to raising the C2S content of the cement, thereby lowering the amount of early heat evolution and also reducing the early strength, but not the long-term strength, okay? Also, the activation energy for the pozzolanic reaction is about 30 kilojoule per mole. So since pozzolanic reactions have an overall increase in solid volume, the porosity of the paste will eventually be reduced, resulting in a higher strength and durability compared with a plain paste of comparable reaction. So that is really the major benefit we get from the use of the SCMs or the pozzolanic materials in this context here. You know, other than the economic factor, the environmental factor, the improvement in the hydrating product, or the product of the hydration, in terms of the lower permeability and denser structure and higher long-term strength, those are excellent benefits we get from waste materials, basically. Okay, so let's see how we monitor the reactions or the pozzolanic reactions. You know, the extent of a pozzolanic reaction can be followed by monitoring the decrease in the calcium hydroxide over time. The results of such an analysis are shown on the figure in the next slide. I'll talk about it in a minute. So in theory, it is possible to completely react all the calcium hydroxide formed by regular hydration, but this really seldom happens in practice. So theoretically it's possible, but not the case in reality. In fact, it is important to realize that the slow rate of pozzolanic reaction requires a prolonged period of moist curing if the full benefits of adding a pozzolan are to be realized. Okay, so without sufficient moist curing, the pozzolan will mainly act as a non-cementitious filler. So this is really something for the practicing concrete professionals, the site engineers and the construction professionals to remember the benefit of moist curing, because almost every concrete mix you will deal with on your site will have some type of a pozzolan. At the minimum, you will have a class F fly ash, maybe microsilica in some high performing concrete. But remember, moist curing is essential in this case to realize the full benefit of these pozzolans. Also, the pozzolanic reaction is more temperature sensitive than the regular hydration and can proceed, you know, quite rapidly under steam curing. So that's something also to remember if you are dealing with precast elements and where the concrete elements are being steam cured. So let's, you know, look at this graph I talked about earlier. You will see here time versus the relative amount of calcium hydroxide formed. In the cases where we have, you know, this control mix, this is just cement without any substitution. Here we added fly ash. Here we added silica fume. Here we added calcined clay or metakaolin. So basically, look at the case of silica fume, basically versus fly ash, where the consumption of the calcium hydroxide is much, much higher. The case of metakaolin being the highest, of course. I'll explain why in a bit. So basically what you take away from this is the high reactivity of silica fume and calcined clay. So a measure of the reactivity of the pozzolan is the pozzolanic capacity, which is usually tested by direct reaction of calcium hydroxide and monitoring the consumption of lime or strength development over time. Okay, so comparisons are given in this table here. I'll show it in a minute. Okay, which basically, shows that the Class C fly ash has a lower capacity than Class F because of its high lime content, the Class C that is. The higher alumina content of a pozzolan means higher capacity because, as I mentioned earlier, calcium aluminate hydrate products may form and they have high lime demand. So the higher alumina content, as the case of the calcined clay or the metakaolin, will have higher demand or they will show higher consumption, higher capacity, because of the added alumina will require additional calcium hydroxide. Also, again, there is a major provision of the ASTM specification, something called the minimum strength activity index, which requires a 75% strength to be gained compared to the control mix at 7 and 28 days, as determined by ASTM C311. I'll show a table coming up later in the lecture about this. Okay, so back to that, to this table here, and shows there is a comparison, as I said, between, this is basically the pozzolanic capacity, which is measured by the consumption of calcium hydroxide, milligram per gram consumed. So basically, as I said, notice the Class C fly ash has less capacity than the Class F because this one higher in lime content. The higher alumina content of a pozzolan means higher capacity because of the formation of calcium aluminate hydrate phases. Look, this is actually easily demonstrated in the case of the Class F and the metakaolin. I mean, the silica fume has higher amorphous silica than the metakaolin, but of course the metakaolin has higher alumina content, and the Class F also has higher alumina content. That's why the consumption of the calcium hydroxide may be higher in these two cases due to that, which is some more calcium hydroxide is consumed for the formation of the calcium aluminate hydrate products. So let us discuss the individual materials, the pozzolans. First, let's start with the fly ash. Fly ash is the most extensively used material, and rather the most extensively used SCM, material in terms of pozzolanic material. And it is, basically the inorganic, non-combustible residue of powdered coal after burning in power plants. So basically the molten particles are swept out of the furnace. Let's go back here. Let's go to this slide. So basically the molten particles are swept out of the furnace. Here is the furnace. With the stag gas and collected by electrostatic precipitators after cooling right here. Okay. Fly ashes are, employed in a variety of construction and many ready mix companies add fly ash routinely to their concrete. So although their motivation is mainly economic, fly ash is being less than maybe half the price of the cement. The addition of fly ash has many technical benefits as discussed earlier, and we will discuss, of course, later. It is estimated that over 250 million tons of fly ash are produced each year in the US, far more than can be used in concrete. Okay, so some fly ashes are not suitable for use in concrete for various reasons, particularly some that derive from lignitic coals from the western United States. Those are not suitable for use in concrete. As power companies also turn to scrubber systems to remove sulfur dioxide from stack gases, many fly ashes become mixed with the scrubber products and contain free lime and calcium sulfates or sulfites. Okay, and that also render them not suitable. So these materials cannot be used in concrete, as for obvious reasons. So it is advisable to purchase fly ash from a reputable supplier to ensure predictable and reliable performance. Okay, so that's the message you have to remember about fly ash. Of course, in your case, as a customer for a ready mix supplier, just make sure you read and understand and make sure that whatever mill certificates for fly ash being used comply with your job specifications, and you are able to flag any inconsistencies or any non-compliances of the materials we just talked about, that's just being containing sulfides or that anything of that nature. Okay. Okay, so more about the fly ash. As we said, it has been used for more than 50 years in concrete. According to ASTM C215, the definition of fly ash is the finely divided residue that results from the combustion of coal and that is transported by flue gases from the combustion zone to the particle removal system, as is shown here. It's also called pulverized fuel ash, PFA. It's again an inorganic, non-combustible byproduct of coal burning power plants, as I said. Approximately less, or maybe half the cost of, or less than that of cement. Can be used up to 50% replacement of cement, and slower reactant than most SCMs. Okay, so this is the schematic showing. This is from electric generating station and shows a schematic of how fly ash is collected. Okay, so we have two classes of fly ash, C and F, as we have been mentioning. For the chemical composition shown here, and also please refer to the previous slides where I have talked about their chemical composition. The ASTM oxide limits are shown in this table right here. Basically, this is according to ASTM C618 classification, class F. Normally, we said from bituminous and anthracite coal, and these are the chemical limits: SiO2, Al2O3, Fe2O3, 70%. For class C, 50%. And these normally from some bituminous and lignite coal. And these are the oxide, or the chemical composition in general. We see the difference here in the silica content between the class F, or the low calcium fly ash, and the high calcium, and of course the calcium. Look at this and look at this. Okay. For determining the amorphous content, we use the XRD analysis, as I have shown earlier. Okay, so just to summarize some more the comparison between the class F and class C. Class F is derived from anthracite or bituminous coals from eastern US. Class C derived from lignite or subbituminous coals from western United States, particularly Wyoming and Montana. Class F, slower rate of reaction than Class C. This pozzolanic, the Class C, pozzolanic and hydraulic reactions because of the calcium, the calcium oxide content. And it's typically faster rate of reaction than Class F fly ash. Typical composition for Class F, less than 10% calcium oxide, more than 50% SiO2. For the Class C, more than 20% calcium oxide, 30 to 50 SiO2, as you can see here. One more thing, as I mentioned earlier, be careful of the carbon content, especially in air entrained concrete, because the carbon affect the air entraining capability of the air entraining admixtures. Okay, so again, reading the mill certificate for the fly ash being used is key by the engineer. Okay, so the physical characteristics, mainly solid spheres with some hollow stenospheres, as shown here. This is an SCM micrograph. The particle size between 5 to 20 microns. Surface area 300 to 500 square meter per kilogram. Density 540 to 860. Specific gravity 2.2 to 2.4, less than that of cement. The color ranges from off-white to light gray, as you can see here. Okay, the next pozzolan we will talk about is the silica fume. The silica fume is basically a byproduct of the manufacture of silicon metal and alloys. The material is formed by vapor phase oxidation in the stack gases and collected in bag houses. It is estimated about 200,000 tons of silica fume are produced each year in the US. This is a schematic showing how the silica fume is collected. As you said here, basically these are electrodes. This is a crystalline quartz Si2 carbon. This is for the manufacture again of the silicon alloy. Okay, this is the bag house, the stack right here, and that's how we collect the amorphous silica. Okay, the ASTM-C 1240 definition for silica fume, basically a very fine pozzolanic material composed mostly of amorphous silica. As I said, it's produced by electric arc furnaces as a byproduct of the production of elemental silicon or ferrosilicon alloys, also referred to as microsilica or condensed silica fume. So remember these terms. As I said, 200,000 tons produced in the US. The typical cement replacement values between 5 to 15%. It's very expensive. It is estimated it's being like 4 times the cost of cement. So its use is not really economical. It's purely technical and probably some environmental benefit, but it's not economical in this case. Okay, we talked about how it is obtained, where it is obtained from, the silica fume, how the product is supplied, or in what forms we get it. If you remember, I said it has to be slurried because it's very fine and sticky. So it's produced as undensified, very fine powder. It's very fine, very sticky, and easily inhaled. I mean, I worked with it. It's not really easy to handle. Or it could be densified as the agglomerated form, we talked about it, or a slurry. So the chemical and physical properties, we said before, it's about between 85 to 98 SiO2, which is being amorphous. This is oxide content, but being high amorphous content. The SiO2 content dependent upon the type of alloy being produced. Its physical characteristics, very small spherical particles. Particle size being between 0.1 to 0.3 micrometers. That's very fine. It's easily inhaled, really. The surface area extremely high, as you can see. That's why it's very reactive. Its density between 130 to 430 kilogram per cubic meter. Specific gravity less than cement. It's about 2.2. Its color generally dark gray in color in the normal form. Okay, so we have other pozzolans I will mention here, the commonly used. We have the metakaolin, basically, this is calcined clay, again at 700 to 900 degrees Celsius. A typical cement replacement about 5 to 15%, similar to the silica fume. Particle size 1 to 2 micrometer. Again, it's highly reactive due to its small particle size, high surface area, and also the amorphous silica is highly reactive, and the presence of aluminum or alumina. Its chemistry about 55% SiO2, 35 to 45% alumina, and that's why it exhibits more pozzolanic capacity, as we have shown in the earlier slides. Also, we have the rice husk ash, another commonly present pozzolan, but not very widely used in the US. This is, again, highly reactive pozzolan obtained by controlled calcination of rice husk. The field burnt rice husk is almost crystalline in nature and makes a weak pozzolan. So to obtain high degree of pozzolanicity, a good control is needed while burning. The rice husk ash usually contains large amount of unburned carbon, which might adversely affect air entrainment. So about 90 million tons of rice husks produced worldwide each year, but less than 2% of that are produced in the US. That's why I said it's not really commonly used. Nonetheless, it is used, and it's very reactive, and it gets good results as far as the concrete properties. But again, care has to be exercised in selecting the material, making sure the material has been processed correctly, and the key is the chemical and physical analysis we have to do on any proposed product to be used in your concrete and your project. Okay, the particle size between 10 and 20 micron, also higher than the silica fume and the metakaolin, but nonetheless is still considered fine. It has it's very reactive or highly reactive, about 85% SiO2. So if it is prepared and burned, produced with controlled burning, then it is a good material. Okay, so we talked about the pozzolans. Let's talk about slag. Slags are residues from the metallurgical processes, either from the production of metals from ore or refinement of impure metals. They are derived from lime-based inorganic fluxes used to extract impurities from metals, which solidify on cooling. The slags used in concrete come from the blast furnace production. That's, the term ground granulated blast furnace slag. From the blast furnace production of iron from ore, when, getting the iron from its ore. When cooled slowly in air, the molten slag crystallizes to form inert calcium magnesium silicates, such as millilite, which of course is no use, or merwanite, and monticelite, and smaller amounts of calcium silicates. So slag must be rapidly cooled or quenched to form a hydraulically active calcium aluminosilicates glass. Okay, so quenching is done using water in one of the two processes. First, granulation or pelletization. In the granulation process, though, the molten slag is broken up by water jets and then immersed in water. So about the 4 millimeter sized granules are then ground to cement fineness. But there is a newer process which basically consumes less water called pelletizing, which is shown in the figure I'm going to show in a bit. The smaller granules, less than 4 millimeter, after that are ground for use as mineral admixture. The larger pellets, which are porous and partially crystalline, can be used as lightweight aggregates. They cannot be used as mineral admixture because they lack the amorphous glassy nature. So to be hydraulic and hence a useful admixture, blast furnace slag needs to be quenched and ground. Remember that, okay? So this is a schematic, shows where the slag is obtained. It comes, here the granulated or pelletized slag. Basically, this is the steel making process. This is where the charge or the raw material comes in, and these are the processes that goes through, and that's where we get slag from. Okay, so this is for the steel making, the pig iron. This is a schematic showing the pelletizing process of for quenching slag. Water jets cool the molten slag before, and as the stream is fragmented by the rotating drum, as you can see here. These are the spray jets. This is the slag. The slag comes here. This is the pig iron, and this is a rotary drum, and it shows we have pellets and granules here. Okay, and that's where the water is collected. So it's physical let me go back. Physical characteristics, we said the particle size less than 45 microns, surface area 400 to 600 meters square per kilogram, density about 1050 to 1375 kilogram per cubic meter, specific gravity higher than the others, about 2.9. The shape is being angular particle shape. Its color generally white to off-white color. Okay, so about the chemistry of the slag. The blast furnace slag, we said, rich in lime, silica, and alumina. So the typical oxides, we talked about this in the previous lectures, by mass percentage of the oxides: calcium oxide 35 to 40%, 45, silicon dioxide 32 to 38, alumina 8 to 16. We have also magnesium oxide and ferric oxide 5 to 15 for the magnesium oxide, 2%, less than 2% for the ferric oxide, and also we have sulfur in small quantities. The ASTM C989 limits the amount of sulfur as sulfide to 2.5% and sulfate to 4%. So there are limits. When you get ML certificates to read it, to verify it, make sure you are aware of the ASTM C989 limits. Okay. Also, if you are in doubt and if there is evidence that requires it, you must require XRD, X-ray diffraction analysis, to make sure you have enough amorphous glassy content, which is typically indicated by this diffuse band. As you see, this is granulated slag and this is poorly quenched slag, and see the difference in the amorphous content, and see the crystalline products present here. This one will not be suitable for use as a mineral admixture, the top one. Okay. So let's look at the reactivity of the slag. Reactivity can vary widely from slag to slag. Although it is known that glass composition is an important factor, there is not, as I said, a reliable quantitative relationship between slag consumption and its reactivity. Okay, it's an indicative characteristic, but not necessarily a hard, reliable quantitative relationship. The ASTM C989 assesses reactivity. Remember, this is the one I talked about before. Assesses reactivity based on determining the strength of mortars made with 50 slag cement blend, basically 50% slag, 50% cement, as compared relative to the strength of a pure cement mortar, as you can see here. Okay? So basically, at 7 days, there is no requirement. At 28 days, the relative strength should be 75%. Of course, this is for the average. This is not less than 70% for the individual cube. And here are for the various grade 80, grade 100, and grade 20. So this is a relative strength test that could be performed to make sure the slag really gives the results that are expected of it. Okay? And I also mentioned, if you remember, about the pozzolans, which is a STMC 311, something of similar nature about the strength, relative strength index. Okay, slag use really dates back almost, more than 100 years. So about 70 to 80, I said before, its cost comparable to the cement, but it could be on the range of 70 to 80%, depending on your locale and how it is produced and the demand for it. The typical replacement values of the cement between 20 and 70%. These are the physical properties which actually I mentioned on a previous slide. Right here, they are listed, so I'm just listing them here again for reference. This how the material looks like. It's white to off-white color, and this is magnified an image magnification under a microscope for how the slag looks like. Okay, so how slag hydrates and how it works. The ground granulated blast furnace slag is a mineral admixture with both, as I have been saying, cementitious and pozzolanic properties. Okay, it is classified as a hydraulic cement in some codes. Be aware of that. Okay, but in that case, an activator is necessary to hydrate the slag. The activation of the slag hydration can be done in one of the following ways, and I mentioned that. Maybe the alkali activation is used, and for example, by caustic soda, which is calcium hydroxide, or the calcium carbonate, or sodium carbonate, sodium silicate, etc. The products formed in this case are calcium silicate hydrate and some calcium aluminate hydrate and calcium aluminate sulfate hydrate products, the gyelenite. Alkali activation alone is used only in special applications. And again, this one cannot just be used in the common concrete applications, only in special applications due to the presence of alkali in this case. The second method is the sulfate activation, which is not common for obvious reasons. For example, by using gypsum, hemihydrate, or anhydrite. The products formed in this case, calcium silicate hydrate, ettringite, and aluminum hydroxide. And again, their care must be exercised when using any of these activation because of their potential adverse effects on the concrete, if they are used in the concrete, which I said they are not. Slags, are most commonly activated by Portland cement, where calcium hydroxide formed during hydration is the principal activator, with alkali hydroxides, playing minor role, or if at all. So basically, the use in the common sense what we are familiar with. The slag is used as a mineral admixture, as a replacement of cement for the various benefits we get from other pozzolanic material. Yes, it exhibits some cementitious behavior, and those could be used in special applications, especially if needed an activator. But for the context of this class, the slags are just activated by the Portland cement, and they work as a mineral admixture. Okay, so I will stop here for this lecture, and on the next lecture, which will be the third and final lecture for the SCMs, we will discuss the influence of the SCMs on the concrete properties. Okay, thank you for listening, for watching, and I will see you next time.